Imagine using the sun itself as a giant magnifying glass to peer at a planet in another star system. This isn't science fiction. It's the remarkable idea behind the solar gravitational lens. According to Einstein's theory of general relativity, any massive object like our sun bends the fabric of space. Light travelling near the sun doesn't go straight, it curves around the sun's mass. In effect, the sun's gravity bends light the way a glass lens bends a beam in a telescope. It can focus the light from a distant object into a more concentrated form. It's like using the curved surface of a wine glass to focus a candle's glow from across the room, except here the glass is an invisible warp in space, and the candle is a distant star and its planet. What makes the sun particularly useful as a lens is its sheer mass and proximity. Smaller objects like planets bend light too weakly, and more exotic massive lenses like black holes are too distant or impractical. The sun is right here, readily available as a cosmic scale lens. If we line up a distant target, say an exoplanet, directly behind the sun from our viewpoint, the sun's gravity will bend the planet's light around it. All those bent light rays converge on the other side of the sun, forming a focused region known as the focal line of the gravitational lens. For the sun, this focus begins at roughly 550 astronomical units away. That's about 82 billion kilometers, or 550 times the distance from Earth to the sun. To put it in perspective, Neptune, the outermost planet, orbits at about 30 AU. Pluto is about 40 AU at its farthest. Even Voyager 1, the farthest human-made object, has reached only about 160 to 170 AU after 45 years in space, not even 1/3 of the way to this gravitational focus. 550 AU is way out in the dark, far beyond the known solar system. But if a spacecraft could reach that distance and align itself with a distant planet on the opposite side of the sun, it could use the sun's gravity as an immense cosmic telescope. The physics behind the solar gravitational lens is mind-bending yet elegant. Light from a distant world spreads out in all directions. When those faint rays skim past the sun's gravity bends them inward. If the alignment is just right, the light that gets bent from all around the sun will form a halo of light known as an Einstein ring. From the spacecraft's point of view out beyond 550 AU, the sun would appear as a black circle, assuming the spacecraft blocks the sun's blinding glare, surrounded by a glowing ring of distorted light. That ring is actually the smeared image of the distant planet, focused by the sun's gravity. Importantly, a gravitational lens doesn't have a single focal point like a simple magnifying glass. Instead, it has a focal line. Beyond about 550 AU, the light remains focused along an extended line. A probe anywhere along that line, say at 600 AU or 800 AU, can still capture the lensed light. The catch is, the spacecraft must stay very precisely on that line of focus. Straying even a little could mean missing the thin ring of light. The focus beam is incredibly narrow. Estimates say on the order of just a kilometer or two wide by the time it's out there. Navigating a tiny spacecraft to stay within that 1 mile wide stream of light is a formidable challenge. So how would the spacecraft use the sun as a lens? Unlike a normal telescope, you're not using a mirror or glass to form an image. Instead, the spacecraft carries a coronagraph to block the direct sunlight, and a detector to measure the Einstein ring of the target planet. By moving around and down the line of focus, the probe can sample different parts of the ring. Essentially, you're looking at the warped, ring-shaped image of the planet, and then using math and computational tricks to reconstruct the original picture. It's a bit like receiving a shredded picture and piecing it back together. or listening to an echo in a canyon and figuring out the original sound. Over time, as the probe scans the ring from different angles, it can gather enough data to algorithmically rebuild an image of the distant world. In essence, the sun's gravity does the focusing, and our spacecraft's brain does the image processing. This is how a spacecraft at the Solar Gravitational Lens can turn the sun into the most powerful telescope imaginable. Why go to all this trouble? Because the payoff is spectacular. A chance to actually see the surface of an exoplanet dozens or even hundreds of light years away. Today, even our best telescopes render Earth-like exoplanets as barely a pixel of light. With the Solar Gravitational Lens, that single pixel could blossom into a detailed portrait. The SGL could boost the brightness of a distant planet by a factor of around 100 billion, and achieve an angular resolution of order 1/10 of a nano-arcsecond. In practical terms, that means distinguishing features on the planet as small as tens of kilometers across. In other words, a telescope using the sun's lens could make out details roughly on the scale of cities. We could map continents and oceans on the distant Earth-like world. We could see polar ice caps or bands of clouds swirling in the alien sky. A dim, unresolved pinprick of light would become a rich, discernible disk, a real place with features. Imagine gazing at an exoplanet and actually seeing the contrast of green and brown land against blue seas, or the white spiral of a hurricane system in the atmosphere. By collecting the light into a spectrum, we could analyze the planet's atmosphere in detail, looking for chemical fingerprints of life, so-called biosignatures like oxygen or methane, or even signs of technology, technosignatures like unusual light patterns or atmospheric pollutants. The SGL effectively turns a modest telescope and detector into a planetary observatory, powerful enough to do remote reconnaissance on worlds that would otherwise be impossibly distant specks. It's like upgrading from a blurry 1x zoom to an ultra-sharp 1000x zoom on the universe's camera. If the solar lens were used to look at Earth from say 100 light years away, it could theoretically produce an image where each pixel is on the order of a few tens of kilometers. That's enough to discern the outline of continents and large islands, the presence of widespread cloud systems, maybe even large moon-sized features. We could create the first true map of an Earth-like exoplanet long before sending any starship there. And the wonder isn't only visual. By staring through the solar lens, humanity could also listen to the light from that world for signs of what it's like. We could perform spectroscopy to detect water vapor, measure the planet's rotation by watching weather patterns move, perhaps even catch the glint of sunlight off alien oceans. In a very real sense, the Solar Gravitational Lens could allow us to observe a distant Earth as intimately as our astronauts observed our home planet from the moon, turning that distant pale dot into a world with recognizable features, and possibly even hints of life. Of course, this grand cosmic observatory doesn't come easy. The challenges are as vast as the distances involved. First and foremost, distance and travel time. The focal region of the sun's gravitational lens starts at about 550 AU. Getting there is an epic journey. For context, if a spacecraft launched today using conventional chemical rockets and gravity assists like the Voyagers did, it will take many decades if not centuries to reach 550 AU. Voyager 1, travelling about 17 kilometers per second, around 38,000 miles per hour, has been cruising for nearly half a century and hasn't even reached a third of the required distance. We clearly need a faster ride. Mission concepts for an SGL probe envision using advanced propulsion, for example a solar sail that harnesses the pressure of sunlight to accelerate a lightweight spacecraft to tremendous speeds. By performing a daring dive close to the sun and unfurling a solar sail, a small probe might reach exit velocities on the order of 100 to 150 kilometers per second, over 300,000 miles per hour. That's on the order of 10 times faster than Voyager. Even at such speeds, we're talking about 25 to 30 years of travel to get out to the focal region. This is a mission you start knowing it might be your children or grandchildren who see the results. Then there's the navigation and alignment challenge. As mentioned, the usable focal tube of the SGL is only a kilometer or so wide. A spacecraft must hit a bullseye in the blackness of space 550 astronomical units away, aligning with both the center of the sun and the moving target star light years away. Tiny errors in trajectory could leave the probe off target with nothing to see. Mid-course corrections would be needed over decades, meaning the craft must have extremely precise guidance. Once it's in position, it has to station keep within that narrow beam of focused light. At 550 plus astronomical units, the sun's gravity is weak. The probe is barely bound to the solar system at that distance, and even a gentle push from the light pressure or a trickle of interstellar gas could nudge it off the line. Thrusters or even additional light sails might be needed to maintain alignment. Communication and control pose another big hurdle. A spacecraft at 550 AU is astronomically far, literally. Radio signals take about 3 days to travel one way. If something goes wrong, ground controllers won't know for days, and any command we send takes days to arrive. Essentially, real-time control is impossible. The probe must be highly autonomous, able to make its own decisions and adjustments using artificial intelligence. We'll have to trust the spacecraft to navigate itself through the void, correct its course, calibrate its instruments, and maybe even cooperate with sibling craft if we send a swarm, all without immediate human intervention. Power and instrumentation also become tricky out there. At 550 AU the sunlight is incredibly faint, roughly 1/300,000th of the intensity at Earth. Solar panels would produce negligible power, so the probe likely needs a long-lived nuclear battery. It also needs a high-contrast coronagraph or starshade to blot out the direct sunlight, which even from 550 AU will far outshine the Einstein ring of the target planet. The solar corona, the sun's outer atmosphere, is bright and can swamp the signal, so the telescope's optics and detectors must be sensitive, but also very well shielded and calibrated to pick out the faint ring of planetary light buried in the sun's afterglow. Finally, there's the patience required in data gathering. Even once the probe is in position, building a high-resolution image is not instant. The spacecraft might need to move slowly across the light ring, gathering photons for months at each position. One concept suggests it could take weeks or months of integration time to get enough light at each sampling point. To assemble a megapixel class image of a planet, you might be collecting data for years. It's like trying to photograph a dim scene by taking a long exposure, except here you may need long exposures, piece by piece, to mosaic together the whole picture. This is an endeavor of extreme persistence. Humanity would have to invest in a mission that might launch, cruise for 3 decades through lonely interstellar space, then spend additional years studying one speck of light. All the while, everyone back home must maintain support and wait for the payoff. It's a grand, long-term bet on our future. It sounds like a sci-fi fantasy, but serious scientists and engineers are already sketching out how to make it real. NASA's Jet Propulsion Laboratory, JPL, has been studying mission concepts for a Solar Gravitational Lens mission, especially over the last decade. One leading advocate is Dr. Slava Tureshev at JPL, who, with colleagues, has published detailed studies showing that an SGL mission is not just theoretically possible, but within reach of near-future technology. In 2020, a team led by Tureshev completed a Phase 2 study under NASA's innovative Advanced Concepts program, exploring how a mission could achieve direct multi-pixel imaging of an exoplanet using the SGL. They demonstrated through analyses that a probe with roughly a 1-meter telescope and a coronagraph, once beyond 547 AU, could indeed capture and reconstruct an image of a habitable Earth-like exoplanet, resolving features on the order of tens of kilometers. The study even outlined a potential roadmap, launching a lightweight spacecraft, possibly a swarm of smallsats, using solar sails to attain the high speeds needed to reach 550 AU in a reasonable time frame, on the order of 25 to 30 years. The idea has also drawn in talent from outside NASA. The Aerospace Corporation, a non-profit space research organization, has been working with JPL on SGL mission architectures. They've proposed a clever string of pearls approach, sending multiple small spacecraft in a series like pearls on a line, each group leapfrogging outward. These nano spacecraft would carry tiny telescopes and communication relays, use solar sails for propulsion, and rely on AI to operate far from home. As one batch reaches a certain distance, it can relay data back and possibly guide the next batch. This reduces risk. Losing one probe doesn't kill the mission, and also spreads out cost and development. In fact, the SGL project was one of the first to receive an NIAC Phase 3 award, signaling that NASA sees enough promise to invest in maturing the concept further. Some optimists suggest that a technology demonstration mission could launch in the 2020s or early 2030s to test key elements, and a full-scale mission might be mounted in the 2030s or 2040s. It's important to stress that as of now, the Solar Gravitational Lens mission is still conceptual. We're in the visionary stage, drawing up blueprints and running simulations. No official mission has been approved or funded at the billion-dollar level it would likely require. But the fact that NASA and other institutions are actively studying it means that it's more than a fantasy. It's a real physical possibility, given enough will and time. The dream of imaging an exoplanet's surface has gone from the pages of science fiction novels to the pages of peer-reviewed engineering papers. People are working today on navigation algorithms, high-velocity solar sail designs, and data processing techniques that might one day let us unveil the face of an alien Earth. Picture a tiny spacecraft, silent and determined, coasting in the interstellar dark nearly 2 light days away from Earth. The sun is just a feeble glow behind it. Out of the craft's camera view, the sun's disk is hidden behind a coronagraph, leaving only a ghostly ring of light in the blackness. That ring is the light of an exoplanet. Photons that left a distant star bounced off a faraway planet's clouds and continents, and, by a quirk of gravity, have been bent around our sun to end up here, whispering their information to our awaiting detector. As the spacecraft slowly pivots and moves, it maps out that ring, collecting the ancient light into an image. Bit by bit, line by line, a picture forms, the first portrait of a world around another sun. It might appear first as a pixelated patchwork of colours, perhaps blue oceans, white swirls of atmosphere, brown-green landmasses. With time the resolution sharpens. We recognise the telltale outlines of coasts and maybe the sparkle of an ice cap. We see day and night areas, perhaps even the flicker of clouds dispersing after a storm. In that moment, humanity would no longer be imagining what an exoplanet might look like. We would truly be seeing it through our extension of eyes across the galaxy. It would be a profound milestone, like when Apollo 8 astronauts first saw the Earth rise above the moon's horizon, or when the pale blue dot photograph showed Earth as a tiny mote in a sunbeam. But this time, the pale blue dot could be someone else's planet, and we are the ones gazing from afar. The Solar Gravitational Lens opens up a door in the dark, offering a looking glass through which to behold the unknown. Philosophers and poets have long wondered what it would be like to find another Earth, a mirror of our own world. Science has given us the means, in theory, to seek that mirror and study it. The journey will be long and the task difficult, but the very attempt speaks to something fundamental about us. We are creatures of curiosity and hope. We build cathedrals of glass and metal and send them into the void, all for the chance to know what lies beyond the next horizon. Using the sun as a telescope is a bold declaration that despite the darkness and distance, we believe in our capacity to reach further. One day, perhaps in the not so distant future, a human will look at a picture of an exoplanet swirling clouds and alien seas. Not an artist's impression or a blur of pixels, but a real image brought to us by a patient little probe at the edge of our solar system. They might remember a time when such a thing was only a dream, and they'll know that dream was made real by people who dared to turn the sun into a looking glass, aiming it at the cosmic unknown, driven by a simple longing to see with our own eyes the wonders that until now have been hidden in the dark. Out at 550 AU, the sun becomes a telescope, and a distant world becomes a map. If that vision moves you, lock on to the frequency, subscribe, ring the beacon, and share this with someone who loves the unknown. And tell me below, if you had one shot with the Solar Gravitational Lens, which would you image first, and why? Keep your receivers on, and tune in to the Omega Signal.